Hello everyone, we are a database group from Tsinghua University. Today, we will present our work interactive cleaning for progressive visualization through composite questions. Let us start with an overview of the typical data analytics pipeline. First, the user may collect data from multiple sources and then transform and clean the data for analytics. However, the visualization results are not always exact and good. One common reason is that real-life data is dirty. Moreover, it is too expensive to completely clean a dataset and then for visualization or any other analytics task. Let us see an example. We have a publication dataset collecting from 6 data sources such as Google Scholar, DBLP. We want to visualize a bar chart to show the total citations of each conference. Due to various types of errors, the visualization is incorrect. For example, outliers affect the height of the bar. In this work, we consider 4 types of data errors: tuple-level duplicates, synonyms, missing values, and outliers. However, visualization is not necessarily dirty, even if the data is dirty. Consider another example. It visualizes a pie chart that shows the proportions of total papers by year. Although data is dirty, the pie chart is not affected by dirty data because the proportion of the number papers by year is the same as ground truth data. The true reason is that the visualization distance is too small. Therefore, we have some observations from examples. First, data cleaning is expensive. Second, some data errors may not significantly affect the visualization result. Therefore, can we just clean visualization-aware data errors to reduce the cleaning costs and speed up the visualization analytics process? We study a new problem that is progressively turning bad visualizations into good ones by interactive data cleaning. Now, we have a dataset with some errors, and we study how to clean visualization-aware errors to progressively improve the quality of visualization. There are 4 main challenges in this work. First, how to quantify the impact of cleaning visualization-aware errors. Second, how to quantify the visualization quality between visualizations before and after the data is cleaned. How to interact with the user to clean the various types of errors, and how to select the most beneficial cleaning questions. For the second challenge, we propose to use distance functions to measure the visualization distance so as to quantify the improvement of visualization quality after a round of cleaning. The distance functions can be earth mover's distance, Euclidean distance, and so on. For each type of error, we can use the existing techniques to detect and generate repairing candidates and ask the user to check. For example, for tuple-level duplicates, we employ entity resolution techniques to detect duplicates and use active learning techniques to select questions to interact with the user. We call such questions as single questions. However, it is hard for a user to precisely answer a data cleaning question without enough context. Interactive data cleaning systems typically provide more information to the user beyond only one data error. Moreover, it is also observed that different errors may impact each other. Therefore, we propose to use one graph model to organize different types of errors. Now, we introduce errors and repairs graph, an undirected weighted graph. In the graph, each vertex represents a tuple, each edge with weight denotes that the associating 2 vertices are possible tuple-level duplicates or synonyms. Those vertices in the same color mean that they have the same synonyms. Now, we address the third challenge by using the composite questions graph. A composite questions graph is a connected induced subgraph of an errors and repairs graph. The user can interact with the composite question graph to provide feedback. For example, the user can approve the edge to denote its associated 2 vertices are the same tuple-level entity and synonyms. This is the solution overview of our work. First, the user needs to specify a visualization query on a dataset. The visclean RST needs to run off-the-shelf data cleaning tools to detect different types of errors and generate possible repairs. It then builds an errors and repairs graph to organize the detected data errors and possible repairs. It then selects the most beneficial composite questions graph from the errors and repairs graph based on the benefit model to interact with the user in each iteration. After getting feedback from the user, it will repair data errors and refresh the data visualization. The above steps repeat until the budget is used up. This is the front end of our system.
Next, we show a quick overview of our system. After that, we will give more technical details.
First, we can upload and select a dataset for visualization. Then we can browse the selected dataset. This is a database papers dataset with 6 attributes, which contains tuple-level duplicates, attribute-level duplicates, missing values. Next, we specify a visualization query to generate a bar chart that shows the top 10 venues ranking by total citations. We can see that the bar chart is incorrect due to various data errors. The visclean system will automatically detect data errors and generate a composite questions graph in the back end. The selected composite questions graph will be shown in the interaction panel. In the graph, each node represents a tuple. Each edge with weight denotes that the associating 2 nodes are possible tuple-level duplicates or attribute-level duplicates. Those nodes in the same color mean that they have the same synonyms for the x-axis of the bar chart. For each edge, the user can CONRM the edge to denote its associated 2 vertices are the same tuple-level or attribute-level entity, or split the edge to shows they are not the tuple-level or attribute-level entity. For example, when the mouse moves on node 302, we can see that the attribute for node 302 is ICDE'20 and the attribute for associating nodes is VLDB. Therefore, we can click the red button to split all edges connecting to node 302 to denote there are not the same tuple-level and attribute-level entities. After clicking, the graph will be updated immediately. We continue to interact with the system. For this subgraph, we can see the attribute of the blue node is sigmod, while the attribute of its associating nodes is VLDD. Therefore, we can conclude that the tuple-level entity and attribute-level entity of the blue node is not the same as those black nodes. Thus, the user can click the red button to split these edges. We continue to interact with the system. After several interactions, the user can return the label answer. Then, the system will repair errors and update the visualization. After 14 iterations, we can see that the bar chart is very similar to the one generated by ground truth dataset. Then, the user can save the cleaned version of the visualizations and dataset. Next, we will introduce how to select the composite questions graph. We first discuss how to quantify the benefit of a composite question graph. Given a composite questions graph, the user can operate the graph to provide feedback. For example, the user may confirm the edge T1, T2 in probability P. After this operation, it will result in a new version of dataset D2, and the visualization will be updated by D2. Therefore, the expected benefit of a user operation can be computed as a probability multiply visualization distance. Formally, we can sum the expected benefit of each operation to measure the benefit of asking a composite question graph. After we know how to estimate the benefit of a composite questions graph, we now introduce the problem of composite questions graph selection. Given an errors and repairs graph and an integer k, the optimal composite questions graph selection problem aims to compute a connected subgraph with k vertices with maximal benefit. Unfortunately, we have proven that this problem is NP-hard by a direct reduction from the clique problem. Therefore, we present a greedy algorithm to compute the composite question graph. The basic idea is that we compute the subgraph with large benefits as candidates greedily and incrementally. This is an overview example of our algorithm. First, we use the benefit model to compute the edges benefit of the errors and repairs graph. We assume the size of the composite questions graph is 4. Since we want to incorporate edges with large benefits into composite questions graph, we sort edges based on the benefit in descending order and iterate on each of them. In the first iteration, we select edge B since it has the maximal benefit. In the fifth iteration, we select edge A and add its 2 vertices into the vertices collection. Now, the size of the vertices collection is equal to 4, hence, we construct a subgraph G1 and compute its benefit. After iterating all edges, we construct 2 subgraphs, and we select the subgraph with maximum benefit as the output. We used 3 datasets for the experiment and conducted 18 visualization tasks on those datasets. We tested 5 algorithms for question selection problem, 2 of them are our proposed algorithms. We concisely show an end-to-end evaluation of our system in this presentation. We used the Earth mover's distance as a metric for evaluation. The EMD can quantify the visualization distance between current visualization and the ground truth visualization. The smaller the EMD is, the better the visualization quality is. As shown in the figures, we can see that the EMD for all visualization tasks decreases in the interactive cleaning process. Let's show more details using the first visualization task. The visualization task Q1 visualizes the top 10 venue ranking by total citations. The initial visualization is very dirty due to various types of errors. We need to ask hundreds of single questions to clean the entire dataset to produce the ground truth. In our system, we just use 15 composite questions to clean it and get a result that is very close to the ground truth. We can make a similar observation on the pie chart. We make 2 observations from this group of experiments. First, VisClean can significantly improve the visualization quality with a small budget. Second, cleaning different visualizations generated from the same dataset needs different budgets. In this paper, we have studied the problem that is progressively turning bad visualizations into good ones by interactive data cleaning. We have presented an errors and repairs graph to model all possible errors and repairs. We have also proposed to use the composite question, that is a group of single questions, to be treated as one question to ask the user. Finally, we have devised an effective and efficient composite questions selection algorithm that asks the most beneficial question to generate the best visualization results. Experimental results on real datasets have shown that our methods can generate high-quality visualizations by asking a small number of questions. The above is today's presentation. Thank you for listening and welcome to Ask Questions.